Imagine structures built 2,000 years ago that remain standing today while modern buildings crumble after mere decades, their secret lying in a formula we still cannot perfectly replicate. What you are about to discover reveals how ancient Roman engineers created a concrete so superior to our modern version that it actually grows stronger over time, a technology lost for centuries that we're only now beginning to understand. Standing at the edge of the Mediterranean Sea, you can still see ancient Roman harbors with concrete structures submerged in salt water for 2 millennia, growing harder and more durable while modern marine concrete deteriorates within 50 years. This is the extraordinary story of Roman concrete, a lost technology that allowed the construction of architectural marvels like the Pantheon with its massive unreinforced dome, aqueducts that still carry water, and harbor installations that have outlasted everything we build today. The Romans called the concrete opus caementicium, and it became the foundation of an empire that built structures on a scale and with a longevity that modern engineering struggles to match even with advanced technology. From approximately 300 BC until the fall of the Western Roman Empire in 476 AD, Roman builders constructed thousands of structures using this remarkable material, creating architecture that defined Western civilization. The Pantheon in Rome, completed in 125 AD, features a dome spanning 143 feet made entirely of unreinforced Roman concrete, and it remains the world's largest unreinforced concrete dome nearly 2,000 years later. This architectural marvel has survived earthquakes, floods, wars, and 2 millennia of weathering while maintaining its structural integrity, a feat that seems almost impossible given that modern concrete structures often require extensive maintenance after just decades. Roman aqueducts, bridges, and harbor installations scattered across the former empire from Britain to North Africa continue to stand, with some still performing their original functions after 20 centuries. The secret to this extraordinary durability lay not in any single ingredient but in the specific combination of materials and the precise understanding of chemical processes that Roman engineers developed through centuries of experimentation. If you find these lost chapters of ancient innovation fascinating, subscribe to Hidden Minds and hit the notification bell to discover more forgotten technologies and overlooked achievements that history left behind. Check the link in the description for scientific studies, chemical analyses, and additional resources about Roman engineering marvels that modern science is still trying to replicate. Roman concrete consisted of 3 primary components: volcanic ash called pozzolana, lime derived from heating limestone, and aggregate materials like volcanic rock, broken pottery, or rubble, mixed with seawater in coastal applications. The key ingredient that made Roman concrete unique was the volcanic ash, particularly the reddish-brown pozzolana found near Mount Vesuvius and similar volcanic deposits throughout the Italian peninsula. This volcanic material contained reactive silica and alumina that created chemical bonds far superior to anything in modern concrete when combined with lime and water, producing a material that underwent remarkable chemical transformations. When Roman builders mixed pozzolana with lime and seawater, a complex series of chemical reactions began that would continue for centuries, actually strengthening the concrete as minerals crystallized within its molecular structure. Modern Portland cement, invented in the 1820s and used universally today, works through entirely different chemical processes that produce a material that begins deteriorating almost immediately after curing. Contemporary concrete is strong in compression but weak in tension, requires steel reinforcement for large structures, and gradually breaks down through exposure to water, salt, and temperature changes over decades. Roman concrete, by contrast, was placed in forms much like modern concrete but then underwent a slow mineralization process that made it increasingly durable, particularly in marine environments where seawater contributed essential minerals. Scientists studying ancient Roman harbor installations at places like Portus near Rome and Caesarea in Israel have discovered that the concrete has been growing stronger for 2,000 years through a process called mineral precipitation. When seawater penetrates the porous Roman concrete, it dissolves some of the volcanic ash components and then reprecipitates them as interlocking crystals of tobermorite and philipsite, minerals that actually fill cracks and strengthen the material. This self-healing property means that Roman marine concrete becomes more resistant to fracturing over time, the exact opposite of modern concrete, which develops cracks that widen and weaken the structure through repeated exposure. Research published by scientists at the University of California, Berkeley in 2013 revealed the precise mineralogical composition of Roman concrete and identified the chemical reactions responsible for its extraordinary longevity. The study found that Roman concrete contains a rare mineral called aluminum tobermorite, which forms through the interaction of seawater with volcanic ash over centuries, creating an incredibly strong and stable crystalline structure. Modern concrete lacks this mineral entirely because Portland cement chemistry doesn't support its formation, meaning our concrete cannot develop the same self-strengthening properties even if exposed to seawater for centuries. The Romans understood through empirical observation that different volcanic ashes produced different results, and they carefully selected materials based on the specific application, whether terrestrial structures, underwater foundations, or marine harbor installations. The architect and engineer Vitruvius, writing in the 1st century BC, provided detailed instructions for making concrete in his treatise De Architectura, describing the properties of different volcanic ashes and the proper ratios for various construction applications. Vitruvius specifically noted that pozzolana from the Bay of Naples area produced the best concrete for underwater construction, advice based on generations of practical experience with marine engineering. Roman builders recognized that their concrete needed time to cure properly, often leaving structures to harden for months or even years before placing them under full load, a patience rarely seen in modern construction. The environmental benefits of Roman concrete are also significant, as its production required heating limestone to only about 850 degrees Celsius, compared to the 1450 degrees needed for Portland cement. This lower temperature requirement meant Roman concrete production generated substantially less carbon dioxide, and the material's extreme longevity meant structures didn't need to be rebuilt or extensively maintained as modern buildings require. Scientists estimate that if we could replicate Roman concrete for modern construction, we could reduce the cement industry's carbon emissions by up to 85% while building structures that last centuries longer. The cement industry currently produces about 8% of global carbon dioxide emissions, making it one of the largest contributors to climate change, a problem that Roman concrete technology could potentially help address. Despite decades of research, modern engineers still cannot perfectly replicate Roman concrete because the exact volcanic ash compositions used by Romans are not fully understood, and the precise mixing and curing processes remain partially mysterious. Additionally, Roman construction methods were labor-intensive and time-consuming, requiring careful selection of materials, precise mixing, and extended curing periods that don't align well with modern construction timelines and economic pressures. The knowledge of how to make Roman concrete was lost during the collapse of the Western Roman Empire when political chaos, economic disruption, and population decline ended the transmission of engineering knowledge from master to apprentice. As Roman infrastructure crumbled and wasn't replaced, later medieval builders lacked the technical expertise to maintain or replicate Roman construction methods, instead using simpler techniques with inferior long-term results. For over 1,000 years, the secret of Roman concrete remained hidden in the structures themselves, their composition a mystery that modern science is only now beginning to fully understand. The rediscovery began in the 20th century when archaeologists and materials scientists started analyzing ancient structures using techniques like scanning electron microscopy, X-ray diffraction, and advanced chemical analysis. These investigations revealed that Roman concrete was not primitive or inferior to modern materials, but was in many ways superior, a humbling realization for engineers who had assumed continuous technological progress. Current research projects are attempting to recreate Roman concrete for modern applications, with some success in laboratory settings, but scaling up production and gaining regulatory approval for new construction materials presents significant challenges. The Getty Villa in California and several other institutions have constructed experimental structures using recreated Roman concrete formulas to test their performance and gather data on long-term durability. Some researchers are investigating whether modern volcanic ashes from locations like California, Iceland, or Italy could substitute for ancient Roman pozzolana, potentially making authentic Roman concrete production economically feasible. Others are exploring whether industrial byproducts like fly ash from coal plants could provide the reactive silica and alumina needed to recreate Roman concrete chemistry without requiring volcanic materials. The European Union has funded research projects investigating Roman concrete as part of efforts to develop more sustainable building materials that reduce carbon emissions while improving structural longevity. What makes the loss of Roman concrete technology particularly poignant is that it represents knowledge that was systematically developed over centuries through careful observation, experimentation, and refinement, then vanished almost overnight. The Romans didn't understand the modern chemistry behind their concrete, but through empirical methods they discovered optimal formulations that we, with all our scientific knowledge, still struggle to perfectly replicate. This suggests that ancient peoples possessed sophisticated practical knowledge that complemented their theoretical understanding, achieving results through experience and observation that modern science approaches through different methodological paths. Roman concrete also reminds us that newer technology is not always better technology, and that assumptions about continuous progress can blind us to valuable knowledge from the past. Walking through Rome today and seeing 2,000-year-old concrete structures standing strong while 20th century buildings show signs of decay provides a powerful visual lesson in the superiority of Roman engineering. The Pantheon's dome, aqueducts still carrying water, harbor installations withstanding millennia of wave action, all testify to an engineering tradition that achieved durability we can barely match. Modern architects and engineers increasingly recognize that understanding Roman concrete isn't just archaeological curiosity but practical necessity as we confront challenges of sustainable construction and climate change. Building structures that last centuries rather than decades could transform construction industry economics, reduce material consumption, and decrease the environmental impact of constant rebuilding and maintenance. The irony is that we have the scientific tools to understand Roman concrete at a molecular level, yet we lack the practical wisdom that allowed ancient engineers to produce it consistently across the empire. Perhaps the greatest lesson from Roman concrete is that technological knowledge can be fragile, that wisdom accumulated over centuries can vanish in a generation if not properly preserved and transmitted. As we face our own challenges with infrastructure decay, climate change, and resource depletion, the example of Roman concrete offers both inspiration and warning about the importance of preserving technical knowledge. The ancient formula that created structures outlasting modern buildings by more than a millennium represents not primitive technology but sophisticated engineering that we are only now learning to appreciate. Every crack in modern concrete, every bridge requiring repair, every structure demolished after a few decades stands as testimony to what we lost when Roman engineering knowledge disappeared into historical darkness. The lost technology of Roman concrete, stronger than ours today, challenges us to question assumptions about progress and reminds us that ancient minds solved problems we still struggle with.